Lesson 2.5. If you remember last class, we were dealing with lesson 2.4. I was hitting this word proportional. I said, hey, a definition for exponentials you need to know is that the x values add and the y values are proportional. Proportional was the word I kept using. It's the definition of exponential that the y values are what type of values? Proportional. Now, if you're like, wait, what did that word mean? I forgot. That means that the values are either multiplying or dividing. You either multiply or divide. That's what it means to be proportional. That's talking about the output values. Which one's output, x or y? The y. The y values will be multiplying or dividing, whereas the x values are, it says equal length input values. What that just means is you're going to have x values that are adding by a common amount, a common addition. Now, why I say addition, not subtraction, is because the x's are always going to increase. So we're not going to subtract there, but the x's will always be adding by a common amount. So if it's 1 every time, then it's 1 every time. If it's 2 every time, then it's 2 every time, so on. It's common. That's what that means. Equal length input. Equal length means same amount. Common. Okay, with that, we'll get started. What's the definition of exponentials? You need to say proportional wise while our x is adding. Okay, proportional wise. What does proportional mean? Our y's multiply and add. And that's why we learned last class that for transformations, if the x's are adding and subtracting, it's going to correspond to the y's being multiplied or divided. Because the definition of an exponential is that y's are proportional, whereas the x's add. Okay. So what this is going to walk you through here, if you read this on your own, is it's just going to tell you sometimes the data doesn't look good right away. And to get around that, we're going to use the average rate of change. So skip down to the end, and I'm going to put down a formula down here. Just box up the average rate of change. The average rate of change can be very helpful for us, especially when it's a calculator active problem. Now, it is my opinion, not a rule, not a law. It's my opinion that on AP exam, if it's the non-calculator, you won't have to worry about this part. So here's what I'm going to tell you. Here's our formula we're going to use today. To find your base, we're going to say base raised to the power of delta x is equal to, and I'm going to write it two different ways. It could be equal to y2 divided by y1, or you could solve using a-rock2 divided by a-rock1. And here's what I want you to write on this. That y2 over y1, this is a formula, so they should be good all the time. But this is less helpful when you have a calculator. It's good without it's good with when you're not allowed to use a calculator. So I'm going to say good W/O, and let me just write without. Good without a calculator. So if you're not going to use a calculator, that's what I would recommend use for your formula. B raised to the power of delta x is going to equal y2 divided by y1. However, if it is a calculator active problem, I would suggest using this. So I'm going to say this is better. So if this one's good, this one is better. And use when calculator is active. Or I should say calculator is required. That's what they'll say in the AP exam. So those are our two formulas we're going to use today. y2 over y1 works whenever you're not allowed to use a calculator. That'll work for you. But if you're allowed to use a calculator, we might need to use a-rock. And I'm going to give you the first three examples are ones that y2 over y1 would not work, which means it would be a calculator problem. So are y'all good to move on? Got that written down? All right, so let's walk through. And I'm going to show you three different problems that are exponential in nature. And we're going to act like this is a non-calculator problem, but we're going to solve with calculator technique. So I'm just going to walk you through the algebra of what we would do with the calculator, if that makes sense. I'm going to walk you through how the algebra works. So first, we see a table. And hopefully by this time I've trained you that if you are not allowed to use a calculator, what's the first thing you're going to do when you see a table? A-rock. And let's do the same thing here. Let's start with an A-rock column. Okay, so A-Rock's the first thing we're gonna do. When I change from 7 to 13, how much am I increasing by? 6. Let's do plus 6, and then we divide by the change of x to be a true A-Rock. It's delta y over delta x. How much my x is changed by? 1. Okay, and then you would go from 13 to 25, which is 12. And from 1 to 2 is a change of 1. Okay, and then how about from 25 to 49? And once again, 2 to 3 is 1, so I did 24 divided by 1. And finally, last one, 49 to 97. Anybody know that math?
48.
48, good. Okay, now why did I do A-Rock? Is it just because I trained you? No, here's the reason. This is exponential. How I know it's exponential is if you look at the A-Rock column, you can see that these are being multiplied. What number am I multiplying to get from 6 to 12 to 24 to 48? I'm multiplying by 2. That's the definition of exponential. The x's are adding, but the y's or the A-Rocks are multiplying. I'm multiplying by 2. Does that make sense? That's going to be my base. My base is going to be 2 on this problem. But here's the problem if we did not do A-Rock. Let's look over here. Is 7 times 2 13? It's close. 7 times 2 is 14, but it's not perfect. Or what about 13 times 2? Does that give us 25? No. So you can see, does y2 divided by y1, would that give me the right values? The answer is no, it'd be slightly off. That's why over here I put that this is good if it was non-calculator problem. If it was a calculator, you would need to use A-Rock, and that's better, okay? That's better. So how do we go from here? Here's how you would go from here. And I'm doing this now as if truly is without a calculator or with a calculator. You would do it this way. You would say that the base is going to be delta x divided by delta x, forgot the x, A-Rock 2, delta base raised to the power of delta x equals A-Rock 2 divided by A-Rock 1. That's the formula I'm going to use here. Now, what is our delta x? 1. How this changes on our A-Rocks is whenever you're doing exponential, you will ignore this denominator every time, or just think about putting it here. You'll never actually use that value. Even if the number was different than 1, you would not use it in this calculation here. So I want you to ignore that. You're only going to use the change of y's. So now, when I plug in, I'm going to say b to the power of, what's delta x? 1 equals my second A-Rock. What do y'all want to say is A-Rock 2? 12, perfect. Let's call A-Rock 2 12. Small c. Let's try this again. There you go. A-Rock 2 is 12. And we're going to divide that by 6. A-Rock 1, which is 6. And 12 divided by 6 is 2. Now that's going to be our base. Need to write over here. Our formula is going to be written in this form today. When we're writing an equation, it's going to be, I'm going to say y1 instead of a. Remember, you could use an a or a y1 times the base raised to the power of x minus x1. And what we're going to learn today is you can also translate these. Remember, you could add or subtract on the y. So I'm going to put plus d over here, which just means however much of a difference I have on my table. That's the formula I'm going to be using. Okay, so now I have a problem on my table. If I multiply these by 2, they don't work. So there's going to be a value that's similar, that's really close to a 7, that if I multiply by 2, it'll give me a number that's really close to 13. And in this particular problem, I'm looking over here, and this is a good place to start. 6 is really close to 7. Is 12 really close to 13? Is 24 really close to 25? Yeah, how much of a difference are there here? 1. I'm going to put it down here. I'm going to pretend like the true y values, instead of a 7, it should have been a 6. It should have been a 6. Now, if it was a 6, I could add by 1 and I'd get my 7. If it were a 6, what would be the true value here? A 12. And then once again, I would just need to add to 1 and I would have a 13. What this should have been is a 24. What this should have been is a 48. And you might not be tracking with me so far, but that's fine. This should have been a 96. Now it wasn't. Here's what you're going to do to write your equation. This first value, whatever the first value is what we're going to call x1. The value that we say this should have been will be y1. And the value, the difference that we need to make it the value that they actually gave us, that's our d. And so once you plug in these three values, and the base, you have your equation. So my equation would look like this. F of x will equal, stay with me, Christopher, here. Y1, what do we calculate as our y1? 6 times the base, which is 2, raised to the power of x minus 0, good, plus 1 on the outside. That was our d right there. And if you wanted to simplify this equation, you could. F of x would equal, you can't multiply those. You have to leave them separate. 6 times 2 to the power of x plus 1. There's our final equation. Now, what we're going to do today is we're going to verify to make sure we did it correctly, because it's kind of like learning some new stuff. We're going to make sure it works. What I want you to do is open up your calculator. Make sure you go to New Document. Please, please, please go to New Document, because we're going to be using some calculations from this in a moment. I want to make sure when I say type in F1, it actually shows up on yours as F1. So home screen, New Document, don't save. That'll clear out all the other equations that have been saved in throughout my other classes. Hit Add a Graph. Let's type in the equation we just solved. We said the equation was 6 times 2 to the power of x plus 1, right? When you press enter, I'm going to do a quick review question. Would you call this exponential decay or exponential growth? That's exponential growth, good. Now press Control T. And I want you to compare these values to the table that we started off with. What can you tell me about the table? Yeah, they're the same. Here's where I think some of my stuff can get confusing if you don't grasp it here. What I'm going to just put here is verified. And for the sake of the notes, I'm going to put verified. What I mean by that is we check the table and the table perfectly matches up. That is the equation. Okay, here's what I think can be confusing. Is I had a y1 up there, and I think more often than not, we might think y1 is 7. But 7 mathematically would not have worked. 7 would not have worked. Why would 7 not have worked? Because if you took 7 as your y1, if 7 was your y1 and you multiplied it by 2, what would you have gotten? 14, not 13. And you could say, well, what if I just put a minus 1 on the outside? It wouldn't work the next time. The next time when you double it, you would have 7 times 2 raised to the power of 2. So it would be 7 times 4, which is 28. And you subtract 1, you would not get 25, you get 27. It would not work. You have to do it this way, which means y1 had to be a 6 to make the table work out right. So I don't have a good term to write down this, but what you're going to hear me say today is what the value of the table should have been. We had a 7. It should not have been a 7, though. We needed to find that first value that makes the math work. Okay? So I don't want to confuse anybody. I'd rather just show you 2 more times before we start asking a lot of questions on it. Okay? Let's try part B. Let's reload and try again. Now, I'm going to pretend for a moment that this is a non-calculator problem where you can use the easy formula. If you took your y2 and divided by y1, what is 10 divided by 2? 5. If a quick version, if it were a test question that was non-calculator, I believe you would say, oh, that's 5, and the next one would be multiplied by 5 as well. What's 10 times 5? 50. Now, do we get 50 there? No, which kind of implies that this would be a calculator problem. But I want to walk you through the algebra once again, okay? So here's our algebra. Whenever you see a table and we're doing algebra, what should be the first thing we do? We're going to add a rock column. How much do I increase by from 2 to 10? I increase by 8, and then what's my change here? 1. Okay, what about from 10 to 34? What do I increase by? 24. What's my change here? 1. What about from 34 to 106? 72. And finally, 216. All right, when you look at the table, does it look like it's adding by a certain amount every time, a common difference, or does it look like it's proportional, meaning it's getting multiplied? It looks proportional to me. Have you already figured out what the proportion is? 3, good. All right, so by formula, if you were going to do it by formula, you would say b to the power of delta x equals a rock 2 divided by a rock 1. By formula, this is the way we do it if we got to use our calculators. What is my delta x? So it's b to the first power equals, what's our a rock 2? 24 divided by 8. By the way, whenever you're using this formula, even if this number was different, don't actually divide. You would, even if it was 8 divided by 2, 24 divided by 2, you would still leave it as a 24 divided by 8. Don't put the denominators in there, okay? Because that'll mess you up. I think. Just don't do it. You just put the power over here, only there. All right. So now, what is 24 divided by 8? 3. Good. The base is 3. So now, let's go over here to the table. If I took a 2 and I multiplied it by 3, do I get 10? What's the problem? Is it too big or too small if I take a 2 and multiply it by 3? It's too small. So that means I need a bigger number over here. So over here, I should have said it this way. If I took a 7 and I multiplied it by 2 in the previous problem, we would have got 14. The problem was 7 was too big, and so we chose a smaller number. It ended up being a smaller number. This time, if I take a 2 and I multiply by 3, is that going to be a too big or too small? Too small. So I need a bigger number than 2. What if I tried a 3? What if I made it 1 bigger? What's 3 times 3? 9. It's still too small. So let's choose a bigger number. What if I made a 4? 4 times 3 is 12. Well, that's not a 10, but it doesn't need to be a 10. If this is too bigger, guess what this needs to be? Too bigger. Let's check the next one. What's 12 times 3? Is this pattern working? That's what the numbers are supposed to be. So now I'll just throw in the math, because if you remember this, it becomes x1. That is my y1. And now what's my d that would make these equal to one another? A -2. That's my d. My d is the -2. All of these would be subtracting by 2 to make that math work. Okay, so let's plug in our equation. They use a g of x. So it'd be g of x equals what? You tell me. What comes first in an exponential? The y1, which is 4 times our base. What's our base? 3 raised to the power of x minus 0. And then minus d, which is -2. You could rewrite this. You don't have to include the x minus 0. What is anything minus 0? Itself. So you can just leave it like that. That should be our equation. And I'm going to verify this now. Okay, the quickest way to verify this, don't clear your calculator this time. Do not clear your calculator this time. If you ended like me on your table, all you have to do is click over to the other side. So move your cursor around, get to the other side, click in there. And if you press the tab button, if you press tab, the equation line will come up. Just press the up arrow and let's change our equation. What was our new equation? 4 for our y1. What did we get for our base? Was it a 3? And then what was our d value? -2? -2. Press enter and then check your table. By the way, is this growth or decay? This would be growth. All right. How's the table look? How do they compare? They're the same. I'm just going to say verified. This is good. The table matches up. Okay, I want to do it one more time, and then if you have questions, you can ask me. All right. Looking at the table. If you just were to look at the table, does it appear to be adding or subtracting a common amount on the y's, or does it appear that it might be proportional? They are getting smaller. Does it look like it's subtracting, or does it look like it might be getting divided? This one's actually going to be dividing. Now, the numbers don't work out perfectly, so what do we do to make the numbers work out right? What do we always do when you first see a table? A-rock. Now, I need to be careful because I'm mixing two different things. We do A-rock when it's a non-calculator problem. However, the problem itself would be a calculator problem. That's what's kind of tricky on this. But I'm going to do A-rock as if it were a non-calculator problem. What's happening to my y's going from 63 to 31 between y1 and y2? We're subtracting 32. And how are my x's changing? Increased by 1, okay? What about from y2 to y3? From 31 to 15? We subtract 16. How much does this change it by? 1. Okay, how about from 15 to 7? And over here? 1, okay? Finally, decreasing by 4, dividing by 1. Okay, look at your A-rock. Do they look like it's an adding, subtracting, or does it look proportional? It's proportional. What's happening each time? Dividing by 2. That's going to be our base. But by formula, if you use this formula, you would say b to the power of, what's my change of x? 1 equals A-rock 2. What's my second A-rock? Negative 16, and you would divide it by your first A-rock. Negative 32. A negative divided by a negative becomes positive. 16 divided by 32 is equal to 1/2. There's our base. Now, if I took 63 and I divided by 1/2, I get 31.5. And that doesn't work. I took 31.5, or 31, I tried to divide by 2, I'd get a decimal again. That doesn't work. If I take 15 divided by 2, it doesn't work. We need to get to an even number first off, so it does work. Let's try either 62 or 64. Which one do y'all want to try first? You want to try 64? Okay, what if we thought it was supposed to be a 64? If you took 64 and you divided by 2, what do you get? 32. Now, what's the difference here? It's 1 bigger. What about here? 1 bigger. That's good. What is 32 divided by 2? 16. Is that 1 bigger? All right, we found our number. It's going to be each one of these subtracted by 1. Does that make sense? So what does 0 represent? That's your x1. What does the 64 represent? What y1 needs to be. And the negative 1, that is our d value. So this equation they call h of x. I'll say h of x equals 64 times the base. If your base is a fraction, let's do it as inside the parentheses. 64 times the base 1/2 raised to the power of. Do I need to put x minus 0? Can I just leave it as x? You okay with that? Just x. And then our d is minus 1. And let's go verify this. Let's make sure that equation is accurate. So again, I'll pull up our equation. Click on this section. You can press the tab key, and then press up to change your equation. We had 64. The base, I'm going to put as a parenthesis here. 1/2. And it was 60. Was it a -1? Okay. Camilla, make sure you're working, please. Try on your calculator. All right. Check your table out. Does your table match up? Does it verify out like it's supposed to? Table look good? All right, last question for you. Looking at the picture here, is this growth or decay? That's decay because the exponential function is decreasing. Very good, it's decay. And with that, I'll now let you try your first DOL. Try number 1 on the back of the packet. By the way, number 1 is non-calculator. Non-calculator. So you can use the easier version of the formula. You do not have to find a rock if you don't want to. Right, as we continue on in this lesson, when we want to write an equation, there's two things you have to know, two pieces of information to write an exponential equation. You have to either know the common ratio, which we frequently will refer to as the base. You want to write base up here. We frequently call the common ratio a base. So geometric, we call it a common ratio. If it's exponential, we call it a base. And the initial value, which the initial value would be referring to x1, y, comma, y1. If you know the base in x1 and y1, you can write the equation. Or if you know two input-output pairs. So meaning you know an x1, comma, y1, and you know a x2, comma, y2, if that makes sense. As long as you have two pieces of information, you can write an equation. Now, with that knowledge, we're now going to move into looking at how this could be used for a free response question, specifically free response question number 2. So free response question number 2 on both the midterm that we just and the final exam that we just took for the first grading period, I gave you a word problem that was something similar to this. It says this: for 0 to 30 minutes, the number of fans inside a large sports stadium can be modeled by this exponential function, where F represents the number of fans inside the stadium T minutes after the doors open. There are 47 people, and cross that out, put fans there. I should have put fans. That's a typo on my part. There are 47 fans in the stadium 2 minutes after the door open, and there's 2,602 fans inside the stadium 20 minutes after the doors open. Part AI. Use the given data to write two equations that can be used to find the values for constants A and B in the expression f of t. Okay, first, what are we supposed to do on AI? We need to write two equations. So to write two equations, you have to know two different points. Did they give us two different points in our problem? Yes, they did. What's our first point they give us? There are 47 fans in the stadium 2 minutes after. Okay, so the first point they gave us, would be, what was, which one refers to your x variable? Is it the fans or the time? Time. Time is the inside. So how much time? At 2 minutes, there's how many fans? 47. We're going to plug that point in first. So we're going to use this equation. What represents f of t? 47. So we'll say 47 equals, we don't know a and b. Those are unknowns. And I'm going to write it the way the equation's given to me, a parentheses b. But we do know our t. What's our t? 2. Very good. That's our first equation. We have to write how many equations? 2. Okay, so now let's write our second equation. So we need a second point. What values are given for our second point? 2,602 fans and 20 minutes. All right, which one is the independent variable? The x. 20, which means our y is 2,602. fans. So let's go plug this in. What replaces f of t? 2,602 are our number of fans. We don't know A, nor do we know B, but we do know how much time this is. 20. If you get that, that would get you a point. Just plugging it into the equation. All right, so now let's find the values A and B. And I would use listen spreadsheets for this. Let's open up our listen spreadsheets. We don't need this anymore. You can clear this out, go home screen, new document. Let's clear out everything we've had so far. And we'll start fresh. We're gonna go to listen spreadsheets. Now, you need to title your columns. You could title them X and Y, but I'm gonna title them, ours were time and minutes for the independent and F for fans. So I'm doing T and F. The two time values they gave us were 2 minutes and 20 minutes. Fans were 47 and 2,602, I believe. Does that sound right?
Yeah.
Great. Now, what type of model is f of t equals a times b to the power of t? That's exponential. Anytime your variable is the exponent, that means it's exponential. So press menu. We're going to go to statistics, number 4, and then stat calculations, number 1. From this long list, the ones that I would be preparing for if I were you is you might have to find a linear regression, a quadratic regression, a cubic regression, or now an exponential. Those are the ones I would really say focus on. This is exponential. When you choose that, it's going to ask you for your X list. This just means what did you title your independent column? What did we title our independent variable? T. T was our input. And what was our output? Our dependent variable? F for fans. It's going to save it to F1. You will use that later. Always note where it's saving it to. Mine's saving it as F1 because I cleared my calculator. Hit OK or press the Enter key twice, and it should give you an equation. By the way, how accurate is our equation here if it says 1? It's perfect. It's perfect. So these are our values right here. Those are our values for our equation, a times b to the power of x. Those are our values right there. So I'm going to take those and copy them over to the notes. How many, it says use decimal approximations. How many decimals should we use? 3 is correct. So I'm going to say you can just truncate 30.089. And B is approximately 1.249. Just going to truncate. That would be worth 2 points right there. Now on this free response question, again, this is free response question number 2. Part A is about writing a model. Part B is going to be about using the AROC. What did AROC stand for again? Average rate of change. So let's go to the next slide, unless anybody has a question over this. Anybody have a question? No, we're good? All right, on the next page, it gives us our part B. It says use the given data to find the average rate of change. What is average rate of change again as an acronym? AROC. Okay. I'm going to first write out our formula. AROC, the formula of AROC is what? Delta Y, change in Y, over delta X, change in X. Our problem does not use the variables Y and X in this problem. We're not using Y and X. Do you remember when we did listen spreadsheets, what represented the Y column? F. So I'm going to say delta F over, what did we use for our X column? T. So it's going to be the change in fans divided by the change of time. So use the given data to find the average rate of change of the number of fans inside a large sports stadium from t equals 1 to t equals 20 minutes. I said t equals 1. Sorry, t equals 2 to t equals 20 minutes. Here's what I want you to do. Put a 1 here. That's t1. This is t2. Express your answer as a decimal approximation. So the t values that we're using are t and 20, 2 and 20. So 20 minus 2. It's always the second minus the first. The second minus the first. So it's 20 minus 2. Now we need to see how many fans do we have at 20 minutes? How many fans do we have at 2 minutes? So we look back over here. How many fans did we have at 20 minutes? 2,602. And how many fans at 2 minutes? 47. Okay. 2,602 minus 47. Let's go do that calculation. Don't clear your calculator. Press Control Dock. Get yourself a new page. Control Dock, new page. I want you to add a calculator. So the AROC is 2,602 minus 47. That's going to find the change in fans. Divided by 20 minus 2. That's going to find the change in the amount of time. When you press enter, it just gives me a fraction. This says to find the answer is a decimal approximation. How do you make your calculator give you a decimal approximation? Control T. And again, we'll take 3 decimals. So there's our first calculation. I know it's kind of small, but that's it. So the first time I typed this in, the calculator said 2,555 divided by 18. And then we press Control Enter, and it said that's approximately 141.944. Now, if you're wondering what is that, what that value is, that's the number of fans per minute that are coming into the stadium. That's fans per minute, fans per minute, because that was our units that we're using. So basically 142 fans per minute are entering the stadium between 2 minutes and 20 minutes. For every single minute, 142 people come in the stadium. You tracking with what that we just found? Okay. Part BII. Here, what you're going to do is you're going to find, using this AROC, we're going to find another value, because the part 3 we have to always compare. So we need to find a value so we compare it to the model. So that's what the part 2 is going to be about. To do part 2, you're going to need to have memorized the point slope form of a line. I'm going too fast. Let me slow down for a second. The reason I'm going to use point slope is because AROC, average rate of change, is similar to what mathematical concept? Slope. AROC is similar to slope, and slope is for a line. So I'm going to use the point slope form of a line for part 2. I'm going to use that formula, which was y equals, do y'all remember the formula? M x minus x1 plus y1. We're going to use this formula. And so when I plug all the values in, x was going to become, I'll just write underneath it. Why don't I just write it down? The AROC becomes our slope. That is our slope. X itself becomes t. X1, therefore, is T1, and Y1 is F1 on this particular problem. That's what I'm going to use here to make my estimate. So I'm using that formula here. So I'm going to have Y equals, what was our AROC? Okay, and we could use the decimal or this, but we'll just go ahead and use the decimal. 141.944, parentheses. Now T, they tell us in this problem, what is our T? 30. That's our T minus T1. Now T1 was up here. What was our T1? 2. And then that will add F1, the amount of fans at 2 minutes. How many fans do we have at F1? It was 47. There we go. Let's go type this in the calculator and see what we get. This will give us the number, it'll estimate the number of fans inside the stadium at 30 minutes. That means if they're coming in 142 people per minute, we're going to find out how many people will be in at 30 minutes into this. So I'm now going to type in, you don't have to type in y equals, but my AROC, 141.944, parentheses 30 minus 2 plus 47. This will give us our estimate of how many fans came in the stadium 30 minutes after the start. Dami, what are you getting? Come on, be typing it in now. 4,021? Very good. And why do we not need a decimal in this one? Because it's people. When we're trying to estimate the number of people, not the average rate they're coming in, but just how many people are inside the stadium. Would we ever have 0.432 of a person inside the stadium? No. So we'll say 4,021. That's our estimate. 4,021 people in the stadium at t equals 30 minutes. That would be our estimate here. And I'll type that in. We're estimating 4,021 fans inside the stadium at t equals 30 minutes. That's our estimate there. Make sense on all that? Okay, finally. When you get to the third part is always going to be a comparison. Now, in mathematics, when you compare something, there's one of three options. A comparison in mathematics is something is either equal to one another, two things are equal, or one is less than the other, or one is greater than the other. Those are the only three options. It says on this part 3, compare the estimate found in 2. This is our estimate, 4,021 fans. Compare that estimate to the value given by the model, f of 30. Do we know what f of 30 is yet? Do we know what f of 30 is yet? Do we know the model f of 30? Answer is no, we don't. We know the model f, but we never solve for f of 30. This is a different estimate. So let's go find f of 30. Pull back up your calculator. This was our model f right here. Did we ever open the new tab and find f1 of 30? Have we done that? No, let's do it now. Remember how this got saved as f1? I told you you will use that later. This is the later. This is part 3 is where you'll use that. Type f1 of 30. This is the exponential model. What does the exponential model have to say about how many people will be in the stadium at 30 minutes? How many people does the exponential model predict? 24,000. How many people did the rate of change predict? Are those equal to one another? No, they're not equal. One is greater than the other, or one is less than the other. Well, let's make sure we write it in the same order. What I do is I just write it out by copy. I don't say compare. Compare is going to be where we say they're either equal, less than, or greater than. So I'm going to write it this way. I'm going to start here and I'm going to say the estimate. I just ignore the word compare. The estimate found in II 4,021 fans is what? Equal to, less than, greater than. What is it? Is less than the value given by the model F30. And what did F30 equal? I should have copied it. Let me copy that value. $24,196 fans. That's your comparison. So the comparison, what does it mean to be comparing? Less than, greater than, or equal to. You use this compared to the model from part A. There's your comparison. All right. Can I show you why this is true now? You have your answer down? Can you stop thinking about the answer? Can you now just take off the I got to get the right answer down mindset. Just take that mindset off for a second, and now just put on the curiosity mindset. Why is that? Why is it we got different values? Can I show you why we got different values? Can I just hopefully this will make sense once you see it. Are y'all ready to switch gears? Okay, why were the answers different? Let me show you. The first model here was what type of a model? Exponential. So if I showed you a picture of the graph, an exponential, remember either looks like a plane landing or a plane taking off. Y'all remember that from last class? I'm adding a page. I pressed up after adding a graph. F1's equation's there. I'll press enter. What I've told y'all is a helpful trick so you can see the picture well. Double the biggest x value. The original x values they gave us were 2 and 20, but then they later gave us a 30. Y'all remember the 30 value they gave us? So what's 2 times 30? Okay, we're going to put 60 right there. See how that's a 60? The largest y value we ever got was this very last number of fans, 24,000 whatever. I'm just going to double 24,000. What's 24,000 times 2? 48,000. That's my exponential model. Is it exponential growth or exponential decay? Growth. That's that model. Now, when we did A-rock does not find an exponential model. A-rock is represented by a secant line. Do y'all remember this? Okay, the equation of the secant line, we basically had it on part B, is we said it was the slope. What was our slope? It was 190 or 141. Say with me, Jessica. 141.944. Was that what our value was? Okay, we said this is true for any x that was between 2 and 20. That was the average rate of people coming in were 141 people per minute, or basically 142 people per minute between 2 and 20 minutes. And so if I press enter, that should be represented by a line. And you could do the intersections. This is just extra here. I don't want to lose anybody. But you could see that these were the points where the graphs cross were the 2 data points they gave me. That's how many people are coming in the stadium on average between 2 and 20 minutes. However, why do the estimates differ? Because they didn't ask for a value between 2 and 20. Where did they ask for a value? I want to make sure everybody's with me. Stay with me. Where did they ask for the last comparison value? What was the minutes? 30. This is between 2 and 20. Let me just put the intersection so you can see it. This is between 2 and 20. That's where these intersections were. I don't know why the calculator goes weird like that, but that's the 2,602. That's the estimate between 2 and 20. They asked us for 30. The reason they're so far off is this is concave up. And if a graph is concave up, this is the unbreakable chain. You have to know unbreakable chain. If a graph is concave up, then its average rate of change will be doing what? Increasing. If you want to find a value at 30, you need to increase your A-rock. Otherwise, the A-rock model is going to be off. It's going to be too low. I'll say that again. If I increase my interval from 2 to 20 to now 2 to 30, my A-rock's going to be wrong because as the graph is concave up, what should be happening to my A-rock? It needs to increase, and that's why the number was so much less. Do y'all remember that? Okay. All right, we're going to look at a DOL. This one on the packet, it's great practice for you. I'll let you practice that on your own some point in time. I want you to try DOL number 3 on the back of the packet. But this problem would be great practice for you for later on. All right, now last class, I introduced a formula A equals PERT, and we were doing financial stuff. And the E I just told you is something in the calculator. It's like pi. Like if I said, what is pi? You would tell me pi is equal to what? 3.14, and that's not exactly equal. So I should do the squiggly here. E is the same way. I gave 3 decimal places, but it's a irrational number, just like pi, never ending, never repeating. You don't need to know it because it's on the calculator, but now if you ever hear the natural base, that's what we're talking about. If we have the natural base, we're using E. So on example 3, what you're sometimes asked to do with the natural base is this. It'll say here on this problem, the number of bacteria B And the particular culture can be modeled by the exponential function b that's equal to all of this, where t is measured in hours. Let a equal function a equal a times b to the power of t be an equivalent expression for b of t. Find the values for a and b. Here's what I want you to know. Frequently with the exponential base, the natural base I should say, with the natural base, we'll have to do this. I want you to see a is 17. That part is easy to determine. You see how a is 17? But our base is no longer supposed to be an e. Whoops, I'm writing the wrong thing. A is equal to 17. But I want you to notice the base is different. B of t is going to equal e of 0.31 t. Now, why do I say that? Because we learned a property last class. The property we learned was called the power property. And it stated this, that when you deal with exponentials, if you have a power that's multiplying, see how I have 0.31 multiplying times t? I could rewrite that as a power raised to a power. And frequently in my class, you're going to be asked to do this. And so here's the math. What I've done is I've separated by power property. I have taken e raised to the power of 0.31 t, and I've changed it to e raised to the 0.31, and all of that raised to the power of t. And at this stage, you could probably tell me what you think the base is equal to. What do you think the actual base is? E to the power of 0.31. So here's what I want to do now. We're going to go to our calculator and just find out what is e to the 0.31, because this will be a constant value. Why do I know it's constant? Because e is a value like pi. So let's go to our calculator. Notice the t's are equal to one another, so you can just ignore that. Let's go to our calculator. We can do a new document. Don't need that anymore. Add a calculator. Our b will be e. Use the e that's 2 buttons to the left of 1. Remember, that's the e we use. To the power of 0.31. What do you get? Okay, and we're going to take 3 decimals for this approximate value here. So we're going to say b is approximately 1.363. Now, what does that mean? That means my equation A, I want you to know that A of t, A of t is equivalent. Let me write it on this part. Sorry. A of t is equivalent. That means that A of t equals B of t. Though they would look different. A of t would be 17 times the power of 1.363 to the power t, but that would equal this equation over here. 17e to the 0.31t. I just want you to know that that means these are equal to one another. That these two equations are equal to one another. Are you tracking with what I'm saying? Do the equations look the same? No, but they're equal to one another. We just changed our base. We learned that last time. By doing a power property, you can change your base. Just as a horizontal translation became a vertical dilation, we also learned that a horizontal dilation can become a change of base. That's what I did here. I changed my base. Okay, now it says find the average rate of change of B of t, and they could have said A of t. They could have done A of t or B of t. Both of these will be the same value. No matter which one you use, you would get the same value from t equals 1 to t equals 7. Okay, so remind me, what's the formula for a rock? Delta y over delta x. And this problem, they say to use B of t. So we're going to be doing the change of the bacteria divided by what represented x in our problem. Whoops. What represents x in this problem? T. So it's the change of bacteria divided by the change of time. And these are probably going to be large numbers. Here's my T1 and T2. Is it the first minus the second, or is it the second minus the first? Okay, I'm going to be lazy. I'm just going to say B of 7 minus B of 1 up here. That's how I'm going to type it in the calculator. Okay, I'm going to be lazy. Let's use the calculator to solve this for us. So go to your calculator. I'm going to add a page, add a graph so I can type in the equation. I'll use the original equation they gave me, 17 e to the power of 0.31. What? 0.31 x. That was our original equation they gave us. I'll hit enter. Is that a growth or decay? Growth. Now what I'm going to do is I'm going to go back over to this page, and I'm going to find my A rock by just using the calculator. I just typed that in as F1. So I'll do F1 of 7 minus F1 of 1 over 7 minus 1. That should give me my average rate of change of bacteria per, I think this is hour. I need to check what the units are. That'll give me the average rate of change of bacteria per hour. Press enter. What are you getting? So approximately 21 bacteria per hour we're increasing by. Yeah, it is hours. It says hours right there. So we're increasing by approximately 20.952 bacteria per hour. 20.952. And this is bacteria. That's what B stood for, bacteria per hour. Because it's positive, it's increasing. So that's kind of gross. Every hour, there's 21 new bacteria. That's going to add up in a hurry. All right, part C. Find the value of T when the number of bacteria in the particular culture is 1,000. Okay, what is 1,000? Is 1,000 a time? Or is it the output? Is it the input or the output? What is 1,000? The output. That is the bacteria. That is the B of T. So what I'm going to do is I'm just going to plug this in for the equation. That's 1,000 right there. So it'd be 1,000 equals 17e to the power of 0.31 t. And again, like I said, you could have used the equation A of t that we found, and it would still give us the same answer because they are equivalent to one another. All right, to solve this one, can I just type that in the calculator, or do I need to insolve that? That would be an insolve. So let's go insolve this. Menu 3.1. It's 1,000 bacteria equals E to the power of 0.31 T. And we're solving for T. And while y'all are typing that in, I'm going to show you that you could have used the equation A, and we still would have got that same answer that we had earlier. I'm using this value right there. And you'll see that you would have gotten the same answer if you used equation A. Both of them would say, what? That's not good. Wasn't that my answer for the base? Well, that's not good. What did I type in wrong? Oh, this one I didn't include the 17. No one told me. Oh, I should have copied and pasted that. That was dumb. All right, let's try this again. 1,000 equaled 17 e to the 0.31. What are y'all getting for your answer? 13 point. Okay, so the only difference I have here is rounding. Because I used this base from earlier. But you can see that the values will, whichever equation you get, you should get the same answer. It's just I rounded my base that I pulled in from earlier. 13.143. And this would be hours. And with that, y'all can try deal well number 2. Deal well number 2. All right, example 4. After 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by this exponential function here, where t represents the number of years since the deer were first introduced. The population of deer increases by 13% each year. Okay, first thing we're asked to find is to find the values of A and B and use these values to write an expression. Now, remember earlier I told you you need to know 2 data points, which this could be here. 50 deers were introduced in a large wooded area. This is our first data point. You could say this has a x1 of 0 or a t1 of 0 and a y1 of 50. So we could say that is our first data point. We could call that t1, comma, I'll do d1 because that's what we have here. And let's see here, we have a rate. It's increasing by 13%. Now here's what you need to know. If we're increasing with exponential functions, if it's decay, it means your base is less than 1. Whereas growth is when the rate is greater than 1. Because we're increasing, we're 13% greater than 1. So to increase by 13%, that means our rate or our base. Let me use base. That would be ratio if we're doing geometric, but for exponentials, we're doing B for base would be equal to 1 plus 13%, which is going to equal 1.13 like that. Okay, so it says find the values of A and B and use these values to write an expression for d of t. Well, as we just said, our A is our initial amount, that's 50, and our base, as stated just right above, would be 1.13. So our equation could be d of t equals 50 times 1.13 raised to the power of t. Now, according to the model found in A, what is the population of deer in the large wooded area after 6 years? Well, that means when t is 6 years. What's the population? So we would say d of 6 would equal 50 times 1.13 raised to the power of 6. So let's go figure out what that is in the calculator. So 50 times 1.13 to the power of 6. And you know, we could have typed this equation in as a graph just so we'd have it stored, but I'm getting approximately 104 deer. That's what I'm going to say here. So the deer at, go ahead and include that in. We'll say this is approximately 104.097, which means we have approximately 104 deer. Approximately 104 deer after 6 years. Okay, so there's our estimate. Now let's check out the next part. Continuing on, it says find the time t when the population of deer in the wooded area is expected to reach 5,000. Now, that is a new d of t value. That is d of t equals 5,000. So if we use our equation, we're going to say that 5,000 equals 50 times 1.13 to the power of t. We don't know that. Now, earlier all class, I haven't done any of these using algebra. I've only used the calculator to insolve. What you would do to solve this algebraically is you're going to do the opposite mathematically. And so the opposite of multiplication is division. You'd first divide by 50, but to finish solving this, you need to know about a logarithm, which we do not know. So for now, I'm going to continue on in solving, but know that we need to know a logarithm to get that answer. So menu 3(1) for now will have to suffice. It'll be 5,000 equals 50 deer times the rate of 1.13 raised to the power of t. We want to know how many years must it take for that to happen, and the answer is approximately 37.68 years. That would be the answer to this one. Approximately 37.680 years. All right. And finally, it says find an equivalent expression d of t where t is measured in months instead of years. So here's the idea. So for our equation that we've had, d of t, where t is in years, was equal to 50 times 1.13 raised to the power of t, because it's 13% per year. Now, here's what's different when we want to do this in months instead of years. We need to change up our rate. So now, basically, for this to be true, t would need to become a 12 when we switch to months. I don't know if this is making sense because it would take 12 months to be 1 year. And so the way that this would work to change the equation to months, I'll do d of months, would equal, you'd take your 50, but now on my formula, if you remember from last class, you would take our rate of 0.13 and we're going to divide it by 12 because that 13% is not per month, it's per year. And now we're going to be dealing with months. And then what you do in your formula is you take the number of times per year times the year. So it'd be 12 times like this. If we were doing this right there, the way I did it would be if we were calculating still in years. So these two should be similar to one another. Let me just show you that right now, that's an M. At the moment, this should still be equivalent to a T. I'm about to change it for the months, how to do that. Okay, so just bear with me just a moment. I want to show you that these two mathematically are equal. If I went and opened another doc and went to graph, and I did 50 times 1.13 raised to the power of x as equation 1, and then I did 50 times 1 plus that 13% divided by 12, the number of times per year, and then did this to the power of 12x. This right here, if we look at our control T, should be very, very similar. Let's look at our two tables. Let me see if it'll slide over. It's not really, oh, there we go. Okay, so we can see both values. I want to show you that these should be very, well, they're not exactly the same. I thought they were going to be exactly the same. Well, what should happen is this should be divided by 12, but over here, and this is because this 13% is not 13% per month. It needs to be divided down to find what percentage is it per month. But now to make this mathematically the same for months, is our months, it takes 12 months to become 1 year. So if T, let me put it this way, if it takes 12 months to become 1 year, so however many months there are, you would divide that by 12 to give you the amount of years. So if you got 12 months, 12 divided by 12 is 1. If you had 24 months, 24. So what I'm going to do over here is I'm going to say this is months divided by 12 as my power. And now I can put this as an M. And this equation should match up perfectly with that one. So let me go make my slide adjustment. And so we're going to do power X divided by 12. Now this would be for months. So it means my numbers are going to look way different. But when I get to 1 year, this is years. This equation was for years. 56.5. I should have this on 12 at 12 months. I should have 56.5. So let's go to 12 and see if we get 56.5. And I'm still not. What am I doing wrong with my equation? I'm going to have to play around here to figure out what I'm doing wrong. But that's the idea. X divided by 12. So when 12, that should be 1. My rate. Okay, I don't need to change my months. That's my problem. I should have just left this as is. Now let me see. Do I get 56 more? I do. Okay. Sorry, I'm overcomplicating this problem. I'm now getting for month, if we're dealing with months, 56.5, which would be 1 year on the original equation. Yep. 2 years, 63.845. That 63.845 should be 24 over here. and it is. And let me just show you one more way. If I did a control dot, I'll get a new page here. If I wanted to find, this is the original equation at 1 year. F2 is now the months, and that would be 12. You see, you get the same value. Or if I did the original in years for 2 years, I would do the second equation at 24 months. And you'll see that these values are matching up. So that's actually how you would do that. I shouldn't have messed with my rate. I should have left my rate alone. That was just, I was just doing too much there. So the rate stays, but what you do is I would just do this. That's the only adjustment you'd have to make. Okay, and so you can try deal well number 4. All right, the last 2 problems we haven't tried yet. Go ahead and open up your College Board and do number 5 and number 6 as well.